Recording.
Is it recording now?
It is.
Splendid. Okay, so today I will give you your first assignment, and I want to talk about dimensional analysis, and hopefully we'll finish that today. And after that, we'll start reviewing classical mechanics so that we can move into statistical mechanics. So, but today I just want to talk about dimensional analysis. So, let's first of all review a little bit of what we have said. Yashar, it'd be great if you could take over so that Nate can devote himself fully to note-taking and activities. Okay, so any questions first of all on what we've done so far? No question. Okay, I think it could be good. Could be a good sign. So one of the important things we said is that we can express every physical quantity in terms of 5 basic dimensional quantities. What are these 5 things? Everybody should know this. Right. Everybody's happy with that. I'm using the SI system, and we know what the SI units are associated with these 5. So the main thing then is to be able to take any physical quantity, whatever units they're given in, and reduce it to these 5 basic things. Okay? Because in this way we can combine things and cancel out things. So we have to always work in the same basic set of units. Now, I want to give you a sheet of information that hopefully will be useful. So these are just physical constants, and we'll be using a number of these throughout the course. It's important that you know some of them. I think that things that I expect people in this class to know certainly is the speed of light, epsilon naught, mu naught. These are just really fundamental things that you need to use all the time. So I'd like you to know both the numerical values for these and the units. And other things that you need to know are Avogadro's number and Boltzmann's constant. So this has units, Avogadro's number does not. Okay. So need to know these. So these are things that you should absolutely know. Things that are not so essential but pretty useful are Planck's constant, I guess you should know. Other things that are useful to know is the charge of the electron and the mass of the electron, but that's less life and death. Yeah, Bohr radius, that's also a good thing to know. I don't know what the symbol is here. A naught. And how big is a hydrogen atom? Of course. One? One what?
One with an hydrogen atom.
But if you want to express in SI units,
I don't know.
I mean, one is actually, it's about an angstrom, right? It's pretty close. So radius is about half of that, 0.53 angstrom. So it's just good to have a sense of the scale of these things. Okay. Other things are less important. In any case, carry this sheet with you, have it in your folder or something, and you'll find it useful for doing homework and other stuff as well. Okay, so much for that. So then the idea of dimensional analysis is simply to take various quantities, express them in terms of the 5 basic dimensional quantities, and then find ways of combining them to give you what you're looking for. And so we did one problem already, which is to find the speed of waves on deep water. And I'd like to do a few other ones today. And hopefully in doing this we'll also get familiar with some physical quantities that will be useful for us later on. Because you all have copies of the notes, right? Yeah. Okay. So the next example I wanted to do was just to ask how large can an iceberg be? Icebergs used to be important because Titanic sank because of one, but they're important in other ways too. But it's interesting to ask, how big are they? And of course that can be pretty small, right? And melt eventually they're all gone. So the minimum size is pretty easy to determine. Maximum size is more interesting. So
are we talking about the part above the sea level or the whole part?
if you know one, you kind of know the other.
Yeah, fine.
Okay, so how do we approach this thing? Well, how is it made? Where do icebergs come from?
Breaks off of a glacier. Breaks off of a glacier.
Right. So icebergs are typically formed by having some piece of land with water below, and there's a glacier here which is moving out. So this is ice, and ice sort of sticks out over the edge of the land. The piece is unsupported, and eventually it breaks, falls into the water, boom, you have an iceberg. That's how they're made. That's where they come from. They typically come from northern Canada. Ellesmere Island is responsible for producing most of these. But the procedure is generally this. So the ice comes out and falls down when it cannot support this big piece that's sticking out. So we are looking for the size, so we're looking for some length. Right? We're looking for length. So if we could do this problem exactly, we end up with the length sum. So what we need to do now is to ask, what are the relevant quantities? So what comes into play here?
Gravity acceleration.
Gravity
acceleration. Gravity acceleration.
The
G.
Yeah, right, the acceleration of gravity. Right? Obviously, the thing breaks because there's a force acting on it, and this joint cannot support that core. So, acceleration of gravity. Good. What else? Mass.
Density.
Density. Yeah. Density is a good thing, right? Mass depends on the size, so expect density, just like before. These guys tend to go together. What else?
Tensile strength.
Stress.
Right.
But I read the notes, so I'm cheating.
Yeah, that's okay. So yeah, obviously it has to do with the strength of the ice, right? If the ice is really weak, it will break easily. If it's really strong, it won't break for a long time. So how do we measure the strength of things, breaking strength?
Shear stress.
Uh,
Shear stress.
shear?
And what is,
You
what do you mean
guys have a
by,
lecture on shear.
what do you mean, how do you measure the strength of things?
How strong is this piece of chalk?
The maximum or sort of pressure that it can hold.
Maximum pressure.
Yeah.
Yeah. So I can squeeze it like this,
Or vice versa.
or pull it. Yeah.
Yeah.
So suppose I want to pull it.
Mm.
I glue the top of it to the ceiling, and I hang the weight from the bottom, and eventually it will break.
Yeah.
And so, now of course, if like a small piece of chalk is going to break easily, a big piece of chalk can support a bigger weight. So we want a material property which is sort of independent of the geometry, and then that will tell us how strong the material is. The same is true of ice. So that's the tensile what? Force? It's not force because small object, big object support.
For force divided by its cross section, let's say, or sort of
By cross section,
of this object.
cross section of area.
Yeah.
Right, area. So what that's right. So what we want is we want to know the maximum stress, force per area that we can apply to until this thing breaks. Okay? So the maximum tensile stress before the thing breaks. And so this has the same units as Young's modulus. Young's modulus is just force per area, right? Stress over strain. And okay, I'd like to see what we can do with these things, see if this is enough. We kind of think it should be enough, right? Because we're describing the force which tends to break it, we describe the strength of the material, maybe it will work. So what are the units of these guys? G has units of acceleration, right? Which is length over time squared. Density,
Mass per volume, or mass per length cubed.
right? Little left. And the stress then, the breaking stress is force per area, right? So it's force per area, and force we can write as mass times acceleration. So we have mass times length over time squared, so that's force, and then we know length squared up here. Good. And now we want to ask ourselves, how can we combine these things so we end up with something having the right units?
A linear Gaussian sense. Separate.
Well, we can do what we did last time, is we can just say, well, suppose it's something like g to the alpha, rho to the beta, y to the gamma. We'll see what we get. Alternative, this is pretty simple. We can just kind of look at it and see how it has to work. So,
Y and rho should be in different parts of this relation, so that m will
right,
disappear.
the mass has to cancel out here. So we have to take the ratio of rho to y. Now, what do you think will be in the numerator?
What was the question? Which one?
We have to combine these guys so that one is on the top and the other is on the bottom.
Okay.
Okay.
Row is going to be on the bottom probably, because
Why?
a bigger row is going to give us a smaller L.
Right. And vice versa. A bigger y is going to give us a bigger length. So we expand the thing to look. So we're just kind of guessing here. The thing should look something like y over rho. Now if we take y over rho, then what do we have? We have a temperature. We have a time squared on the bottom. And so we have to get rid of that.
G on
So we have to put G on the bottom. Right? So will this work? Will this have the right units? So I just write everything out. So we have M, L, T squared, that's Y. And then we have 1 over rho, which is L cubed over M. And then we have G, which is L T squared. So these guys go, these guys go, these guys go. So it works. So these are the relevant quantities. This is how you have to combine them to get something in the units of length. Okay? Now, we could have done it formally. We could have done the same procedure what we did last time, put in the things, make sure that we get the same exponents of these quantities on both sides and determine alpha, beta, gamma. But often in simple cases, you can just do it like this. You can just stare at this and just figure out how the thing has to work. Okay? Okay, so we have a nice result. Then we have to ask, is this sensible? So what is Y for ice? Okay, so we don't know. You have to look it up. And if you look it up, you get 10 to the 7. Okay, and the units are again force per area. And force per area is just pressure. And usually we use Pascal for SI unit of pressure. It's newtons per meter squared, of course, but we call it Pascal. Okay, G, what's G? Actually, I don't mind using it one. And what's the density of ice?
900 kilos per meter cube. Or 800, no.
But
900 kilograms.
it's less than water, right? Water is 10 to the third.
Yeah.
So now we know that ice cube,
I think it's 09.
about a tenth of it sticks out above the water, right? So 0.9 is pretty close, right? So but I just put approximately 1 here, just for simplicity, 10 to the third. So yeah, it's really 0.9 kilograms per cubic meter. And this is approximately 10. So like this is just an approximate affair. So we put these numbers in, we have 10 to the 7 on top. And we don't even have to write down the units because we know that things are going to work out. So it's 10 to the 7 on top, 10 on the bottom for G, and 10 to the third for rho. And so this gives us 10 to the third meter. Is that reasonable? Well, if you think about it, if you think about an iceberg, you only see a tenth of it. So you might see 100 meters sticking out of the water. That's not too bad. So this is sort of more or less reasonable. So this again is, I hope you guys like this approach because you can take really crazy sounding problems and you can come up with really nice results that have physical content. Again, you can say if you're on the moon, and you have icebergs on the moon, G would be smaller, so you can expect to see bigger icebergs. And you can get good numbers as well. So it's a really powerful method, and the more you play with it, the better you get at it. And as I said, the real physics is in identifying the relevant quantities. But there are a couple of problems that are worth mentioning. Is that sometimes when you get relevant quantities and you have lots of them, sometimes it's possible to form dimensionless quantities. Sometimes you have enough things here that you can group them in such a way that you get something that has no units, all the units cancel out. Then you're kind of in trouble because you don't know where this dimensionless thing goes. Okay? This doesn't happen often, but it can happen, and you need to be aware of it. And a classic case, a classic example where this happens is when you're talking about phase transitions, like liquid crystal phase transitions, ferromagnetic, non-magnetic transitions. It turns out that you can combine things in such a way as to get, for example, a quantity like a quantity that has units of temperature, which you call something Tc. So you can have things, intermolecular interaction parameters combining to give you something with the units of temperature. And then, of course, you have actual temperature in your system. So you can have something like T over Tc. And so now this is a dimensionless quantity, and you don't know how this enters into whatever quantity you're trying to calculate. And so it happens, for example, that you end up with a 1 minus T over Tc in the denominator of some expression. So the dimensionless quantity you're calculating is here, maybe. But you have something like this, and this can be huge. This can go to infinity. So this kind of thing can really throw things off. If you had a result like this L made up of simple, some simple combination of things, but then you had something like that multiplying, you could be out by orders and orders of magnitude. But it doesn't happen often. In fact, it happens very rarely. But you need to be aware that that possibility exists. So if you have so many quantities here that you can form a dimensionless group, then you have to be careful. Then you really have to maybe use more physical intuition than simply combining things in this way. In the notes, I discussed this a little bit for the previous case of water waves. If you put in viscosity, for example, then you can make a dimensionless group, and obviously that can be part of the real detailed answer. But sometimes even in that case you can figure out how the dimensionless group comes in by thinking just in ordinary common sense way about what would happen if the viscosity was infinite. What would that do to the speed of the waves? Or the viscosity was zero. And that can tell you, for example, how the dimensionless group appears, this way, or perhaps the reciprocal. So physical intuition can help you even in that case. Okay, but generally speaking, this kind of argument works very well and it's sufficient to give us good answers. Okay. Now suppose you want to know, you don't have access to the library. About these things you know, but this is something that you don't know. So if dimensional analysis is so good, can we figure out what that ultimate breaking stress is, just from dimensional consideration? What does that, first of all, why does a block of ice kind of hang together? Why is it a solid? Why don't all the molecules just fly apart?
Because they hold on together. So
Yes.
there is some interaction until
Absolutely.
some distance between them. So
Right.
if these molecules are close enough, they are firm. The whole ice is firm. When they are far enough, they are already not firm. So they.
Right, but far enough they don't see each other. Okay. But what is the interaction? Why do they want to be close together?
Interaction. Well, it's intermolecular interaction. We can say let it be van der Waals or Whatever.
I don't know though, no, that doesn't, okay, so intermolecular just means, yeah, the thing between two molecules, sure, that's just the name. Van der Waals means something, okay?
Yes.
So, what are Van der Waals interactions? Why do, why do molecules like to be
Induced dipoles attract.
induced dipoles? Right, and where do the induced dipoles come from?
From the other dipoles.
From flotations, they flotate and they somehow interact.
Yeah, it's exactly right. So you have some molecule with an electron cloud, and let's say that this is neutral, but there are quantum mechanical zero-point fluctuations. So the electrons move somewhere, now you have an instantaneous dipole. That dipole fills the whole universe with its field. Another molecule here feels that field, its electrons move, it now has a dipole, that in turn has an effect on the first guy, and it works like that. So that's why things want to be close together. It turns out that if you look at the energy of these two molecules, that energy has a 1 over r to the what in the denominator?
12.
And 6.
12 is the
Six.
number.
6.
6, yeah. Yeah. Goes as 1 over r to the 6. And we'll talk how that comes about in more detail later.
As
So
a
it
1
goes-
over r to the 12 is the repulsion from Pauli exclusion.
Right. That's right. Right. So yeah, so the long range attractive part goes as 1 over r to the 6, pulls them together, and when they're pretty close, the electron clouds start to overlap, and it's Pauli exclusion that keeps them from coming closer than when the electron clouds overlap. That's why we don't fall through the floor, because of Pauli exclusion. So now we understand that the ice sticks together because of these kinds of forces. So this somehow comes as a result of those forces. So now later on we can figure out in detail how those forces arise. But right now we just understand that somehow these attractive forces, and if we knew how big those attractive forces were, or what the interaction energy was, then we could probably sort that guy out. So what is a good measure of the interaction energy of a pair of atoms or molecules?
Temperature of melting.
Right, temperature of melting, exactly right. So you heat up the ice, at some point it melts. It means that now temperature is enough to overcome this strong attraction, and things are now not so tightly locked together. And but we're looking for an energy, kind of, and temperature is not an energy.
KBT.
Yeah, kBT. So it's the Boltzmann constant. So KT. Sometimes people put a B here. I usually don't bother. Boltzmann's constant times the temperature has units of energy, and and this is a measure of the energy on a molecular level. And so if you put the melting temperature here, then that tells you, to a good approximation, what the interaction energy is between two water molecules holding the ice together. So we will rely on this, so this is often a good measure of interaction energy. Okay, so what's Boltzmann's constant? Who knows it? I'm looking up the notes.
138 times 10 to minus 20 30.
Minus 23, right? 1.38 times 10 to the minus 23. So this is, right, so this is a very good thing to know, 1.38 times 10 to the minus 23. And what are the units?
Joules times second, I think.
Joules. Well, if this
No.
has units of energy,
Second.
Kelvin.
joules per Kelvin. Right? temperature is
373, 373, 273, right?
273, right? 273, yeah. So you put 0 there again. If you use Celsius, it doesn't work there. So this is 273. Okay, so this gives you some sense of what the interaction energy is, and that's a really good thing to keep in the back of your head. And then, that KT is the measure of that. And then you see that this is pretty small, right? I mean, this is 10 to the minus 21 joules. On the other hand, there's lots of atoms in it, lots of molecules. So, the total amount is not trivial, but per molecule or per atom, it's not so big. Okay, so now we have an energy here, and if we want to go from an energy to pressure, what do we have to do? What is the
Divide by volume.
divide by volume? Right, that's right. Energy is force times length, it's just doing some work. And if you divide that by volume, length cubed, you get force per area. So that's a really good thing to remember too. The pressure is the same as energy density. Those are the same units. And they often are actually the same. And this is a very useful concept. If you're thinking about radiation pressure from light, for example, then you see that the energy density and the radiation pressure end up being the same units. So if we wanted to calculate then Y, just from the dimensional argument, we have we want to get essentially a pressure here, and we have energy, so we have to divide the energy by volume. Volume of what?
The energy distance of the molecule.
The volume of a molecule. We need a volume in there, and the only thing we have is molecules. So that's a volume of a molecule. So we can roughly, so this is about 10 to the minus 21. And how big is a molecule? We just said a hydrogen atom has a diameter of 10 to the minus 10.
But I think we need to divide not by the size of the molecule, but the distance or the volume per one molecule in the ice whole. In the whole ice. I mean, if the molecule is like this, and they are situated like this, so we need to divide not by this molecule volume, but by this one. So we can take the whole volume of the piece of ice and divide it by the number of molecules of ice in this, let's say, cube. And then find that.
So that's going to be pretty much the same number, right? Because these molecules are really next to each other. I mean, if you had a gas, then sure, the average distance between molecules is much, much bigger than the size of the molecule. But in ice, it's kind of comparable. But you're absolutely right. Well, we need a volume, okay? And that volume has to be something like a molecular volume. So, okay, but so roughly speaking, what are we looking for? What's the size of a water molecule? H2O, when you think about hydrogen is 1 angstrom, oxygen is how big?
I guess 10.
Not that big.
I like it.
It's just a little bigger than hydrogen, actually. It's not much bigger. So, but we are, I mean, if you were to say that it's, I don't know, 3 angstroms or something, then maybe we get 10 angstroms cubed. So we get something like 10 to the minus 29 for the volume. An angstrom is 10 to the minus 10. If you cube that, 10 to the minus 30, like 10 of those, 10 to the minus 29. So this we said is 10 to the minus 21. We have 10 to the minus 29. So we get 10 to the minus, so we get 10 to the 8. Right?
Used to, it is still possible that you have 1 or 2 other error when you get down smaller.
Well, yeah, so we know that we can't get it exactly. We may be out by factors of 2 pi or some other number, so things will Palffy-Muhoray, and we're saying that so this should be basically this energy kBT divided by the volume of a molecule. And so we're saying that this is 10 to the minus 21, and this is something like 10 to the minus 29, maybe, right? If we assume that the water molecule is 3 eggs times an egg, right, when we pack them together. So this would be 10 to the minus 29. And so here we get 10 to the 8. So that's actually bigger than this. Not by much, 1 order of magnitude, it's bigger. And, but you see, it works pretty well, this scheme. So even if you don't know the breaking system, you still make a stab at it. Now it turns out that when things break, they tend to break sooner than you would expect, based only on sort of molecular interaction considerations. Why is that?
Because we don't break it like it's not breaking across this cross section at once. It starts breaking at one point, and then that.
Well, yeah. What is the one point?
I don't know how that's called in English. The word.
Well, explain it in words.
It's like the same when we have that scotch tape. If we try to tear it, just pulling, it's quite hard. And if we cut a little bit on one side, so it's quite easy.
But so, yeah, so things have weak spots that are defects in materials, and things start to break at the defect. It turns out that stresses get concentrated then, and then the crack propagates away. And so things tend to break because of defects sooner than they should. And that's a sort of a complicated problem, because then you have to think about, well, defects, how many are there, how big are they, what is the distribution? There's a biggest defect, that's going to be the one who causes all the problems. There's a weak spot, that's where things go bad. And so the first thing is that things break sooner than you think because of the defects typically. And there were some really beautiful experiments that were done on the breaking strength of glass that were done not that long ago. Basically, people took columns of, forget the guy's name, columns of glass, loaded it, and saw when it broke, measured the ultimate tensile stress, and then made the glass rod thinner, and he found that the strength went up. And that sort of makes sense, because if you have a thinner cross-section, then you would have fewer defects. Kept making it thinner and thinner, and eventually, so plotting y versus the radius, he found that when it was big, the thing was small, and then it increased, and then it eventually plateaued. And this was the value that you would get from the molecular calculation. So if you make things so small that the probability of having a defect is vanishingly small, then you can get to this value that you would predict just based on intermolecular interaction. If it's too big, you have defects. Okay, so, all right, this is a good story. So, you can derive all kinds of interesting and useful results just from dimensional considerations alone. And again, when you're doing exams, it's a really good thing to keep in mind. If you don't know the exact equation that you need, you can often figure out how things should combine to give you something with the units, what you're looking for. All right. Any questions on this?
I have a question, because we estimate the size of iceberg. However, most of the iceberg on the sea we see is cone-like instead of the triangle. So I think because the cone-like of the iceberg, maybe the estimate way maybe a little different with the triangle way. is the now we because the I know if the bracer pull down and the key of the bracer is a little like the cone, so maybe the area of this is bigger. And
You mean it looks
Yeah,
like
yeah.
this? Yeah.
yeah, so
But sure, I mean, our model is not even a model, you know, so we have no real details of the geometry here. We're just asking if you were to do this problem exactly, you know, if you were to assume a shape and you were to calculate it, you would write down the answer, how would it appear? And I think it would have to appear something like this. Now, if you were to make assumptions about the shape, then there would probably be a dimensionless factor in here, which would contain information about the shape, but probably that would be not very different from 1. You know, so maybe 1 or 3 or a half, something. That would depend on the shape. So I agree that, you know, this is really approximate, and a more detailed analysis would give you something with some shape information in there. And probably that wouldn't be a very big factor. Okay? Good. Any other questions? Okay, so let's stop